Okay, so very good. So welcome to today's edition of the video seminar on computational social choice. We have two speakers today, Rida Laraki and our own Bill Zwicker. So Rida is speaking first. Would you like to share the screen?
Yes.
So we have our usual conventions about questions in the chat. So let me remind this to those who may be new. So feel free to ask questions during the chat. So the speaker doesn't commit to checking your questions during the chat. So they may or may not have co-authors in the audience who may help them. But yeah, so if a question is asked in the chat, so I suggest that if it's a question rather than a response or an answer, you type in capital letters question and then ask your question. This will make it easier for the speaker and also for me to find it at the end of the talk, right? And if you feel you are competent to answer the question being asked, or you just want to make a comment, so feel free to engage in discussion, right? So we usually have quite interesting discussions in the chat. Yeah, so Ulle, as always, is setting an example. So this is how you ask a question. Okay, so the usual format is 20 minutes for the talk, 10 minutes for questions. So this can be somewhat flexible. So Rida, will you have someone helping you out in the chat, or are you on your own?
I don't know if my student is here. I didn't check. So I will answer at the end. And at the end, even if we stop, I will try looking at the chat and answering if there are some questions not answered. Right. And feel free, of course, to write to me if anybody is interested. You can write to me just directly to my email and we can discuss.
Okay, so then let's start. So Rida, stable matching games, the floor is yours.
Thank you. So this is a work with my PhD students, Felipe Garrido. So it's about stable matching. All you know, Gale and Shapley model, man and woman. Men have preference over women, women have preference over man. And we would like to match them in a stable way, meaning that no man and woman not matched can strictly improve their utility by matching. So the model have been extended in various directions. Here, one direction which will interest us is the housing markets of Shapley Shubik. So here there are monetary transfers, prices. So men are buyers and sellers, and there are houses. And matching means that a buyer is matched with a seller and they transact at some given price. And stability means that no unmatched, so everybody is getting more than its outside option, which would be zero, meaning that the price should be between the cost and the value for the buyer and the seller. And also no buyer and seller that are not matched can match and increase their utility by finding an adequate price. Gale and Demange extended, and other people extended this model to matching with transfers, and there are also matching with contract. I'm going to speak about it at the end. And the idea is here now transfers can go in both directions, and they are not necessarily linear in utility. So in the three cases, each proved the existence of stable allocations, that this set is a lattice, have a lattice structure, meaning the maximum between two stable matching, when we take the maximum for man, it will be also a stable matching, and it will correspond to the minimum with respect to woman and vice versa. And also there is an algorithm which to prove existence, and usually it is kind of the different acceptance algorithm, and there are many other algorithms that have been devised for that problem. So motivation here is that in real life, when two people interact or are matched, it's not in particular buyer-seller or professor with a university. It's not only monetary transfer that will enter into account. University will, for example, give some conditions for the tenure, how many teaching hours, how many PhD students should supervise, and the professor will have a teaching plan and research plan for the university. So there is kind of, each person has its kind of actions of which he is or her responsible, and they can contract or not. So that's why we're going to study two kind of models. We're going to model these interactions by a strategic game between two players. In one case, they will not contract on the actions, and in that case, they should be playing a Nash equilibrium of their game. And another model, second model, which is the more interesting model I want to present, the second part of this talk, will be the case where players can contract on their actions, meaning that they are commit, they can commit, but still each one is responsible of its action in this interaction. So this is the map of the presentation. So here I'm going to present the model and two stability notions, Nash stability and non-Nash stability, commitment or not commitment. And then in this second part, I'm going to talk about the non-commitment problem. And here are really the most interesting results, the new feature, let's say, of our results. Okay, so the matching game will be man and woman. So if they are matched, so they don't need to be matched, but imagine that a woman I with woman J are matched, then they should play a game. Xi is the strategy set for the man, Yj for the woman, and Ui utility function of player for the man, and V for the woman. The game may depend on the couple. A matching profile will be a strategy for each man, a strategy for each woman, and a matching, meaning a man matched to a woman, and the utility of a player I is look at the woman mu I associated by the matching mu to I, and look at their game and look at the strategy he is playing, Xi, the strategy she is playing, or the contract he is offering, the actions he is ready to take, and why are the actions the woman is ready to take, and this is the utility from their interaction, and similarly for the woman. And also each player will have an individual rational payoff. If the utility is less than this individual rational payoff, he prefers to remain single. Okay. So, and we will have two notions here of stability. So imagine now everybody there is some process that I will not define, and which end up with man and woman matched. Some people remain single, and they have some intended action to play. Okay, so then we will ask two things. Is this situation stable? To be stable, it should be externally stable, meaning that no man and woman that are not matched by this process prefer to be together and have a better payoff. And at the same time, internally stable, meaning that the action that the man is intended to play in the game he's playing is maximizing his payoff, given the action of the woman, and given that he wants this woman to stay, not to go with another man, and vice versa. So it should be it's a stability in the contract between the man and woman. It's kind of Nash stability. In one case, it will be exactly Nash. In the other one, it will be a generalized Nash notion, depending on commitment or not commitment. So now let's suppose that there is no commitment. So they are intended to play. So some referee tells them, you play Xi, you play Yj, but they can if they agree to match, they are going to play, but nobody is supposed to, they can deviate if they want. To be stable, internal stability means that each one of them should be playing a Nash equilibrium. So this is the Nash stability. And external stability means that there is no blocking. So means that first, each one should be getting at least his outside option, his individual rational payoff. And also no pair of players can find another Nash equilibrium, not matched, can find a Nash equilibrium in their game that gives both of them strictly more than the payoff they have actually in the matching. Okay, and we call such an allocation internally Nash stable. And our first result, which is not the most interesting results of the paper, but just to tell you that we can solve this problem if you want. We can show that Nash stable allocations exist if all games we have non-empty compact set of Nash equilibria. So, and also we can prove a semi-lattice structure, meaning that the maximum between maximum with respect to men of two stable matching will be stable. The maximum between two women's stable matching is stable, but what is not true is that the max for man is the mean for woman, and vice versa. So this is not true. And how to prove it? So it's kind of different acceptance algorithm, similar to Gale, Demont, Sotomayor. So imagine men are proposing to a woman. So if a man proposes to a woman which is single, he should propose at least her outside option. If she is not single, if she is with another man, then these two people, so he should propose at least the payoff she has with the man with whom she is married, if he can. if he can, then these two men start to compete like a second price auction. So they start increasing the utility of that woman until one of them is no longer don't want to continue the competition and prefer to propose to another woman. Okay, and you continue like that, and what's happening is that women's utilities are increasing, and that's why the algorithm will converge. And once it's converged, it will lead to an internally Nash stable outcome, because the propositions of man will always be Nash equilibria. They will always propose a Nash equilibrium, and they just will switch between Nash equilibria, and that's why we will have existence. So let me give an example to show why this model is, while it's interesting, probably it's interesting in its own, it's not modeling, capturing what happens if the idea is to extend the model with transfer, then this model is not included in the model I've presented because of commitments. So imagine that we have two, I call them a man and a woman, but it can be a buyer and a seller, and they have an outside option. Their individual rational pair is strictly positive, some delta strictly positive. And suppose they play a transfer game. What is a transfer game? So player one can give a transfer to the man to the woman. It's minus for him, so and plus for her. And the woman can also give a transfer, which is a plus for the man, the minus for hers. And you see that the sum of transfer is 0. So that's the game of transfer. So and it's each player is controlling, can give a transfer. It's an action that the man can do, or you pay the price to buy the house. So this is what you can do in this game. So this is the game they're playing. Imagine that they agree to play this game. So it's a constant sum game. In this game, the optimal strategy for each of the players is which is a dominant strategy in this game, is to beat 0, is to give 0, because the best you can do here, your utility is increasing when you decrease your x here. So each player gives 0, so which implies that the woman will have a 0 utility because x minus 1 is 0, but she being alone for her is given her a strictly positive utility. So there is no stable solution in this game. It's better to remain single. Okay. So the intuition, in fact, what we want to do intuitively here is that the man would like to propose at least delta to the woman, and the woman will accept. But for this to be implementable, implicitly there is some commitment. As before, you transfer the money is received, and then okay, we agree, or you sign a contract or something that makes this commitment implementable. Because otherwise, in this game of transfer, the unique Nash equilibrium in this game is 0. Okay, it's no transfer. So if you want this intuitive outcome, which may be realized by transfers, to be implemented, we should implicitly assume that pair can commit, can sign binding contracts, and this is what we are going to do now. And we are going to study this model in which it's possible to have commitment. So now the difference, external stability means that there's no contract, okay? There's no pair of contracts no players that are not matched by matching can find a pair of contracts without the restriction of being Nash that gives both of them strictly more than their outside option. So this is external stability. And if we look at the example we just did, external stability means that the net transfer from the man to the woman should be at least delta, if the man should give at least delta to the woman for her to accept, and it should not exceed 9 delta, because otherwise the man prefer to remain single because he has 10 delta utility to be with that woman, so he cannot pay more than 9 delta. And so we have a set of externally stable solutions, which would be exactly the prediction of Shapley, Shubik, Gale, Demange models. Okay, and now with internal stability is it's kind of generalized Nash solutions here. What it says is the following: we have internal stability if either we are playing a Nash equilibrium in the game, or if player one, for example, would like to change the contract from x to x prime. Okay, this is the variable he's controlling. Here, the payoff, the man can increase or decrease the payoff is given. here he would like it to pay less to the woman. If he's tried to pay less to the woman, then the woman will not be happy to stay with him and break the stability of the couple. And vice versa. The woman, if she wants to decrease the money she's giving to the man, then the man, if it is possible, it may not be possible because she's doing y equals 0, she cannot decrease, y is already minimal, but if she can decrease, then the man will not be happy, okay? In this example, the unique externally internally stable solution is exactly x equals delta y equals 0. Why? Because if x minus y is strictly higher than delta, if you decrease slightly x, you increase man's utility because this is the payoff he is giving to the one, but you still want to stay with him because x minus y is strictly higher than delta. So the man would like to decrease the x until x minus y is equal delta. Now, if x minus y is equal delta, but not but y is not positive equals 0, then the woman would like to decrease the money she gives to the man still he would like to stay with her, and this implies that at the end, unique possible stable outcome is x equals delta y equals 0. So, Sophie, if you are convinced by this example, let me give another example, which is an auction. You have n buyers, one seller. They can commit to monetary transfers, and there is one indivisible good. It's completely standard. VI, the value for the good for each buyer I, and the seller has a reservation price of C. And we suppose that if the seller accepts the contract to contract with the buyer at price PI, then VI minus PI will be the utility of the buyer, PI minus C the utility of the seller, and if they don't transact, then the utility is 0. Suppose also that we rank the buyers by their values, then you have two cases. Or the cost is higher than the maximum value that a buyer can pay, then there is no transaction, of course, because if there is a transaction, one of them will be the seller or the buyer will not be happy because he prefers to remain single or no transaction and having 0. Otherwise, if V1 is higher than C, then everything between, so the unique external stable outcome are that the price is between V1 and the second highest price or the reservation price, and the buyer one is the one who is doing the transaction. Okay, so that's the unique externally stable outcome, and the unique externally internally stable outcome are the outcome of second price auction. So you see that this mechanism, these two conditions, if you apply them to auction, they will give you exactly second price auction. Okay. Good. So now I'm going to define to see what can we say in the second model with commitments. For any matching game with compact strategy set and continuous payoff functions, so it's really very general. So take any game in finite game in mixed strategies, for example, it will be true. There always exists an externally stable matching profile. So the proof is exactly the same as I did before, except that when men propose to women, they will not propose in the set, the proposition will not be restricted to be Nash equilibria, but there will be any possible profile. And what we do here is, of course, we have a epsilon, which will be, when you draw a proposition, you should increase but at least epsilon the utility of the woman. And so you have an epsilon approximation, and then you take epsilon goes to 0, and that's how you prove existence of a 0, an exact externally stable matching. For the moment, even in the literature of transfer, in the problem studied by Gale, Sotomayor, we don't know how to compute exactly a 0 outcome. We discretize the sets of prices, which correspond to the model we're doing here. So it's an open problem how to compute exactly a 0, an algorithm that gives you exactly a 0. So, and we have a semi-lattice structure. The algorithm converges to the proper Poser side preferred elements. And what is interesting is that if you have strictly competitive games, which is exactly the model studied by Gale, Sotomayor, and all literature on transfer, they are strictly competitive game, a particular case. Then we recover the lattice structure. The maximum for man is equal to the minimum for woman, and vice versa. So now we proved the existence of externally stable matching. We would like to prove to look at. We would like, in addition to have internal stability, for that we are going to define a notion of constrained Nash equilibria, which is a generalized Nash equilibrium notion. So imagine we have an outside option ui0 for the man and vg0 for the woman, which can be their individual rational payoff, and it can also be what they can get in the market. For example, if I can see another woman, she accepts to be with me because I give her more than her outside option, or more than her payoff with a man. And this is the best I can do if I go outside the couple where I am. So we say that xi,yj is feasible with that couple of outside options if both players get more than their outside options. And now what is a constrained Nash equilibrium with that pair of outside options? It's a profile x prime y prime such that it's a profile xi yj such that if player I has a profitable deviation, so he cannot contract with this deviation, because this means that the other person, the partner, will get strictly less than the outside option. So he will not accept the transaction. He will not accept to be in the couple. So in the case of our example before, so if the man proposes to the woman less than delta, he will increase his utility, but the woman will get less than her outside option, and she will not accept, and vice versa. It can be written in that way as an argmax. So utility of the man is the maximum he can get under the constraint of participation of the woman, and vice versa for the woman. So that's really so if you do contract theory, in contract theory, the principal propose a contract to the agent under the participation constraint. Here it's a simultaneous game between each one is at the same time the principal and an agent, and each one wants the other one to be participating while maximizing his payoff. So that's the notion. And now we would like to find the class of games such that for any pair of outside options, if feasibility is guaranteed, meaning that there is a possibility of agreement, players have a contract that gives them more than the outside option, then there is also a constrained Nash equilibrium. There is a generalized Nash equilibrium existence. Unfortunately, not all games will have this property. For example, this is a two-player game in mixed strategies. Take 0 as outside option. So this game has a unique Nash equilibrium which gives to both players negative payoff. So it cannot be the agreement. So now imagine that so feasibility is guaranteed because, for example, if they play TL, both players get strictly more than the outside option. So they can play TL and have more than the outside option. But if they play TL, then player one can deviate from T to M. He increases his payoff from 2 to 3, and the other player will get 0, which is his outside option. So it's a deviation, valid deviation, and so this 2-1 is not stable. It's not a constrained Nash equilibrium. 3-0 is not also a constrained Nash equilibrium because player 2 can move from L to M. He increases his payoff from 0 to 1. And but this is strictly higher than, this is feasible because everybody's getting more than the outside option. So I checked here for pure strategy profile, but it's true for mixed strategy profile as well. And the question is, what is the class of game for which we can guarantee existence of externally stable matching, of constrained Nash equilibria for any pair of outside options? We can prove that this class is actually large. It contains constant sum games, zero-sum games, strictly competitive game. So this covers the class studied in the literature of transfer. It also includes the class of potential game and also the class of infinitely repeated games, meaning that if I take this game and I repeat this game infinitely often, then I will restore existence. So since for example, when a professor contracts with the university, it's a repeated game. So we think that this is the case in many real life situations. When you marry, it's for a long period. When you contract with a buyer and seller, not buyer and seller, but for example, you hire someone in a company, it will be a repeated game. So I think this makes this result interesting. The fact that existence happen in infinitely repeated games. And it's interesting also this model of infinitely repeated game because now we don't need commitment. If we are playing a game infinitely repeatedly, if a player deviates, it's like in the Folk theorem, or in what happens is the punishments could be, I quit you and I will change the partner. So it's no longer needed that we have commitment when we are working with an infinite game. So just to give you an idea about the proof is difficult in all cases except potential game. In potential game, how to prove existence? Just maximize the potential given the constraint of feasibility. You would like that both.
Eating in your question time.
Okay, so let me just finish. I have this is my last slide. So there is an algorithm that implies existence in all the classes of game I defined before. This algorithm starts with an externally stable machine and change one by one couples which are not playing a constrained Nash equilibrium, and each converges. This algorithm converges for all the class of games I just defined. And now we have a second paper, which study complexity in all these cases. So there will be soon, so I stop here, just to say that there is an article in Archive, which is an old version. And in 1 week or two, we are going to put a new version, which include what I said today. And hopefully in 1 or 2 months, we'll put the one with complexity, another paper studying the complexity. And thank you for your attention. I'm sorry for the time I spent.
Right. Okay, thanks, Rida. So let's unmute for a round of applause. So I don't think we had much activity in the chat. So there was a question from Judy that was a clarification question. And then I think it did get clarified. So there's another question now coming from Rohit. So Rida, do you want to read it out loud?
Yeah. Question: does the equilibrium existent result depend on the bipartiteness of the matching instance? And what happens in the roommates model? Interesting question. So we didn't study the roommates, so I cannot answer to this. So here this proposition, it's not, so how to say, it has nothing to do with the stable matching. Take a problem where you have two players, both play the principal agent at the same time. Each one controlling part of the contract, and you want an equilibrium between the contract because each of them has an outside option. This proposition tells you that in this class of games, in this class of interactions, you have existence, and we would like to see why we don't have existence always, because you can write this problem as a quasi-rational inequality problem, and in this quasi-rational inequality problem, all assumptions of existence are satisfied except that the correspondence is not lower semi-continuous; it is upper semi-continuous. It has none. So that's why we don't have existence always. So always in all finite games, let's say, for example, let's like this game in mixed strategies. But existence has nothing to do with the fact that we have a matching or not.
Thanks. Any more questions? Okay, so I suppose I have a question. So when you consider deviations by a pair, by a man-woman pair, so did I understand it correctly that they have to deviate to what would be an equilibrium in their own game?
In the first concept,
yes.
In the first definition, this is what I suppose, because it should be a credible agreement. If a pair of players deviates, and since there is no commitment, the deviation, the contract should be a Nash equilibrium of their game. Otherwise, there is no reason for the other person to respect or not. This was the first concept I studied. In the second concept, they can deviate to anything. Anything that can increase their payoff is acceptable. It's very strong to be if you are externally stable, you cannot find any agreement, Nash or not Nash, which can increase strictly both players' payoff. So it's a strong stability, external stability notion. So there are two models. They don't give the same predictions.
Mm-hmm. Okay, more questions from anyone? Okay, so if not, then let's thank Rida again And so we'll have Bill Zwicker's talk after the break, but first the break. So I think we have 10 minutes, and Dominic will now distribute us among the break rooms.
Can you see my slides?
Okay, so second talk of the session, John Nash meets Jorge Hersch, scale invariant citation indices. So exciting topic. So welcome, Bill.
Thank you, Edith. So this represents joint work with Joseph Freshus and also with Roger Hurl, who's in the audience. I will start by defining the Hersch Citation Index, and then I'll talk about its important property of linear growth. Then we'll turn to a review of the Nash bargaining solution. We'll import ideas from Nash to get a scale invariant version of the Hersch Index and also to get a scale invariant version of a related index defined by Wojinger. We'll look at an axiomatic characterization of the scale invariant Hersch Index, which parallels in certain ways Nash's axioms. And then we'll consider comparing the original versions of these indices with the scale invariant versions in noisy circumstances. So let's talk about the Hersch Citation Index. Suppose Professor R has published 11 papers so far. His most cited paper got 13 citations. What you see, you can see my hand moving here, correct, on the screen? Yeah. So what you see here is the number of citations of his other papers arranged in non-increasing order. And that vector is called his citation record. When you apply an index to a citation record, it returns a number. And the Hersch Index, little h in particular, is defined as follows. It's the biggest integer n, such that the researcher has published at least n papers, each of which got at least n citations. So the first 5 papers here got at least 5 citations, but the first 6 papers did not all get at least 6 citations. So that says, for this example, this Professor R has a Hersch Index of 5. Okay, there's a well-known geometric equivalent posed in terms of the bar graph or histogram. The heights of these bars represent the number of citations we were looking at before, so the highest bar has a height of 13. The horizontal axis represents productivity in terms of the number of papers. The vertical axis represents impact in terms of citations. And the biggest square that can fit under this bar graph is a 5 by 5 square, for the same reason that 5 is the biggest number of that 5 is the value of the Hersch Index. So an equivalent definition of the Hersch Index is that it's the side length of the largest inscribed square for this histogram or bar graph. Okay, so why did Hersch propose this rather than the total area in the bars, which is the total number of citations added up over all papers? Well, the part of the bar graph that sits above the top edge of the red square is called the vertical tail, and that represents perhaps a tiny number of highly cited papers. Maybe Professor R wrote a joint paper with a famous co-author who did all the work, maybe Professor R's thesis advisor, for example, and that's not reflective of the number of citations that his later papers received. The horizontal tail represents a potentially large number of papers that don't get very many citations, which supposedly means that people are not so interested in it. So Hersch's idea was to lop off the vertical tail and the horizontal tail, leaving the square. So lopping off these tails, the idea is that it rewards most highly the citation records that strike an appropriate balance between productivity and impact. So the question we raise is, does appropriate balance here actually coincide with using the square to lop these tails? There are some implications for using the square. It says that the vertical and horizontal tails, in a sense, should be truncated at the same point. And it says that a unit on the vertical axis should be the same size as one on the horizontal axis. In other words, it identifies a research paper with a citation. But when you think about it, in some fields, books are the norm, not papers. And if these represent number of citations of a book, then one book is equal to one citation. And by the famous transitivity property of equality, this allows us to conclude that one research paper is equal to one book, and that's a little bit questionable. So let's look at an actual example. It's not an actual example, it's a made-up example. Suppose Professor A and B are in these fields where you write books, not papers. We expect fewer books than we would research papers, but more citations per book than per research paper. So Professor A has written 4 books, and the least cited book has 150 citations, which is a decent number. Professor B has written 6 books, but they didn't get very many citations. If we apply the Hersch Index in this example, the Hersch Index of Professor A is 4 books, because his 4 books all got at least 4 citations. But for B, the Hersch Index is 5, because his first 5 papers all got at least 5, first 5 books all got at least 5 citations. So B actually gets a higher citation index than A does, and that's doesn't seem necessarily appropriate, especially when you consider the fact that the Hersch Index is actually used sometimes to rank researchers in a field, for example, as a stage in deciding who gets a grant. So you might say this example is kind of extreme and unrealistic. Maybe the Hersch Index shouldn't be used when you use books, but there are milder versions. Let's consider 2 subfields of mathematics: algebraic topology, in which the papers tend to be fewer in number but longer and have more citations. Finite combinatorics is a branchier subject. People write more papers, they're shorter, and you expect them to have fewer citations. Imagine Professor C and D are algebraic topologists, but if you like the many worlds interpretation of quantum theory, imagine some quantum event called the fork in the universe, and in a parallel universe, the same 2 people, C and D, turn out to be finite combinatorists rather than algebraic topologists, and we'll call them C star and D star, but they're actually the same 2 people. So let's take C's bar graph and compress vertically by a factor of 2 to account for the fact that finite combinatorics papers tend to have fewer citations, and stretch horizontally by a factor of 3. So what would that mean? That would mean if originally we had a single bar of height 10, it would now get a height of 5, but then we would take that 1 bar of height 5 and replace it by 3 bars of height 5. So that's how we do the vertical and horizontal changes. So that result is C star's bar graph. This is what C would do in the parallel universe. And suppose we get D star's graph from D's in the same way, using the same stretch and compression factors. Then it's very easy to come up with examples in which in one universe, C gets a higher Hersch index than D, but in a parallel universe, it goes the other way around. And we argue that this says that Hersch's index can distort rankings within a subfield, especially a subfield where the one-to-one relationship between citations and publications violates more severely the publication culture of that subfield. So now I want to talk about the linear growth property for the Hersch index. Hersch used the side length of the square, not the area of the square. So let's talk about why that's the case. He considered a very simple model. I'll call it the SDM, simple deterministic model. You have 2 constants, P for the number of papers you publish per year and C for the number of citations your papers get per year. If P is, for example, 3, then every year on the simple deterministic model, the researcher publishes exactly 3 papers. And if C is 4, then every year, every paper that was published that year or in an earlier year garners exactly 4 citations. So obviously this is simplistic. For any citation index and a researcher, we get a function that says how that researcher's index value grows over time. And Hersch liked using the side of the square because under the simple deterministic model, the Hersch index in the simple deterministic model gives a straight line as a graph. And that straight line has a slope. And Hersch's idea was that you could use this slope to compare a senior researcher with a junior researcher. Of course, the senior researcher is going to have tend to have a higher index, but if you want to factor out the number of years, instead of comparing their indices, you compare their slopes. And under the simple deterministic model for Hersch's index, that slope is given by the ratio of P times C divided by P plus C. And what you notice in the denominator here is that we're adding 2 quantities whose units are not necessarily comparable, right? So physicists should have been cautious about that. Okay, now let's turn to the Nash bargaining solution. 2-person bargaining problem, 2 players, row and column, seek an agreement. Maybe that agreement is to play a pair of strategies in a game, yielding a payoff to each. We have a payoff space or feasible set consisting of a closed, bounded, and convex region, F. I'll say it's contained in the first quadrant. In effect, I'm locating the disagreement point at the origin, for those of you who know the Nash bargaining solution. This is a simplified version. And for any point x in that region, it's x, for any point xy in that region, its x coordinate represents the the payoff in utility to row player, and the y-coordinate represents the utility for the column player. And the problem is to decide on which point, which bargain to strike, which pair of utilities to get. So a local solution is a point in the feasible set F, but Nash was interested in global solutions. A global solution is a function phi that assigns to every possible feasible region a point in that region representing the point that you should agree upon. And Nash suggested 4 axioms for this function: Pareto efficiency, symmetry, invariance on the utility scale changes, independence of irrelevant alternatives. Pareto efficiency says the point you pick should lie on the Pareto frontier. These are the points with the property that you can't simultaneously increase the x-coordinate and y-coordinate and stay in the region. So it's rational to choose a point like that. Symmetry says if you flip the whole region along the line y equal x, you will change the solution, but you'll change the solution by simply taking the flipped value of the original solution. And really what that says is that if you rename R as C and C as R, it doesn't have any effect on the payoff of the solution. So it says the names are not important in effect. Invariance on the utility scale changes says that if you rescale along the x-axis, this has no effect on the y-coordinate of the point you pick. So if this is the original region and we pick this point, then when we scale that region by halving the size of the utility units for the row player, that in effect stretches the region out by a factor of 2 horizontally, then the point we should pick should have the same y-coordinate as it did before. So changing units with which x measures her own utility shouldn't have any effect on y's payoff. And the idea behind this is an expression of this principle that interpersonal comparisons of utility don't make any sense, that there's no common unit for utility of you and utility for me. Okay, I'm going to skip a discussion of independence of relevant alternatives for time reasons. If people have questions about that, I'll come back to it in the question and answer period. Now I want to talk about how we import ideas from Nash to get a scale invariant version. Oh, I want to talk about Nash's solution, sorry. So Nash suggested that we pick the point in the feasible region that maximizes the product of utilities rather than the sum of utilities. And that's the same thing as saying you're maximizing the area of the inscribed rectangle, right? So the theorem that Nash proved is that his solution maximized the product of utilities, satisfies the 4 axioms, and no other solution does. So it's a unique solution. That's the axiomatic characterization. So now how do we use that idea to modify the Hersch index? Well, originally the Hersch index was the side length of the largest inscribed square. That's the same thing as taking the square root of the area of the inscribed square of biggest area. So we simply take Nash's idea, we move it over, and define the scale invariant version, SIH, of the Hersch index to be the square root of the area of the inscribed rectangle of biggest area. That's the same thing as the geometric mean of the footprints of that rectangle on the x and y axes, respectively. So 2 questions. I'll get to the second question later. Right now, I want to talk about how the scale invariant Hersch index behaves for professors A and B. That was the example where A had a lot more citations but fewer books, and A actually got a lower Hersch index than B. If we look at a picture of their histograms, which tend to be long and narrow, the maximal area rectangle for researcher A rises all the way to the height of the least cited book, which was 150. And we wind up taking the square root of 600, which is 24.5. Whereas for B, it rises up to the height of the 5th most cited book, which is 9 citations, has square root of 45 as its scale invariant Hersch index, 6.7. And this does a little bit more like what we might hope or expect to see as reasonable ways of judging these books. Later, I'll talk about what happened in the parallel universe. So Wojinger defined a related index, the W index, and that's the leg length of the largest inscribed isosceles right triangle. We'll see a picture in just a moment. And we can do the same thing for Wojinger that we did to Hersch. We can get a scale invariant version by relaxing the requirement that the inscribed triangle be isosceles. In that case, it has 2 legs, A and B, sitting on the X and Y axes that may be unequal. And we define the value of the index to be the square root of the product of those legs. Okay, here's a picture. of the original bar graph I showed at the beginning. If you want to make it look more like a bar graph, you have to add these vertical segments. Right now, it's a step function. This is the Hersch square. And this is the scale invariant Hersch rectangle. This is the Woginger isosceles right triangle. And this is the scale invariant Woginger triangle. And now we have an axiomatic characterization of the scale invariant Hersch index with 6 axioms. So scale invariant Hersch is the unique index satisfying these 6 axioms. The first axiom, monotonicity, says that if you take a publication record, add 1 citation to a paper, or add 1 new paper with 1 citation on it, that never hurts the value of the index, can't go down. Symmetry says if you take the bar graph for a citation record and you reflect along the line y equal x, you actually do get a new bar graph, and it says the value of the index should be the same for that reflected version. And these 2 axioms are both satisfied by the original Hersch index and also by the original Woginger index. Strong scale invariance says if you take a citation record X and perform a vertical stretch or compression by K and a horizontal stretch or compression by M, then the proportional effect on the value of the index is the same as the proportional effect on some other citation record, Y. And the implications of that are, in our parallel universe example, any index satisfying this axiom will give a higher index to C than to D than if it does this, if and only if it does the same thing in the parallel universe. And therefore, the relative rankings of these 2 researchers won't change from one universe to the other. The max bounded axiom is the one I won't spend much time talking about because I won't have that much time to talk about it, but it selects the scale invariant Hersch index from a much wider class of indexes that includes the scale invariant Woginger index. It's closely related to Nash's independence of irrelevant alternatives axiom in the bargaining problem. Scale responsiveness says that if I look at a citation record consisting of a single paper that has 2 citations, it gets a higher value than a citation record consisting of a single paper that only got 1 citation. And linear growth is more or less the axiomatic version of the linear growth property we're stealing from Hersch's idea. It says that the graph of growth under the simple deterministic model is a straight line, but since it's actually a step function the way we define it precisely, you have to use a pair of parallel straight lines in the official axiom. The distance between those parallel lines is relatively small. Okay, and then this characterizes scale invariant Hersch index. Okay, so now let's talk about something we observed in the Hersch index in practice. There are records you can find online indicating all the Hersch index values for researchers in a country. My co-author Josep looked at this for Spain, and we saw an awful lot of people getting the same Hersch index. So it suggests that there are a lot of ties under the Hersch index, and we wondered whether the scale invariant version could be more decisive. So how did we measure that? We took some simulations in which we took the simple deterministic model and added noise. And what that means is, for example, with p equal 0.125 and c equal 0.32, we every month, because these are monthly figures rather than yearly now, every month we drew an integer, a non-negative integer, from a Poisson distribution that has a mean of 0.125, and we use that integer as the number of papers published that year. And then for each one of the papers that were published that year or in an earlier year, we drew a non-negative integer from a different Poisson distribution with mean 0.32, and that was the number of citations that that paper got that year. Other papers involved independent draws from the same probability distribution. And we also did this for 2 other pairs of parameter values besides 0.125 and 0.32. And we ran 500 pairs of records. So the first of each pair was run this way. The second of each pair was run by giving 10% more to the P and C values. So we ran independently 500 pairs of records, and we asked how many times did we get ties? What proportion of those records were ties? So let's look at Hersch and scale invariant Hersch to start with the original P and C values. We see that scale invariant Hersch index had about 1/10 as many ties as the original Hersch index. So yes, much more decisive. And that advantage persists for the other two parameter choices. So it seems like our instinct that we would get fewer ties is correct. Of course, the problem is that getting fewer ties alone is not necessarily a good thing. Maybe ties are being broken here because of the effect of the noise. And what we're doing is breaking ties that really shouldn't be ties. Are these being broken in meaningful ways? Well, you'd expect if it was the noise that was breaking the ties, then the noise would also sometimes take the person with the higher P and C values and give them a lower Hersch index, if it's the noise that's creating the greater resolution of the scale invariant versions. So we looked at how many reversals there were in this case, strict reversals. And we've, before I do that, I want to discuss what happened with Wojinger, same situation. With Wojinger, in terms of decisiveness, proportion of ties, the effect is even more dramatic because for the numbers we used, the scale invariant versions had no ties for 500, among 500 pairs. Okay, now let's talk about reversals. With the original parameter values, not only does the scale invariant version has fewer ties, but it also has fewer reversals. So that says that we're not just using the noise to break the ties, that this truly represents greater resolution, tie-breaking power of the scale invariant versions. However, as you move to the other parameter values, with the 0.2 and 0.2, that advantage disappears, and the scale invariant versions do about the same in terms of reversals. And with the parameter values that have a higher p-value, number of publications per year, per month, than c-value, the advantage actually swings in the other direction, towards the scale and away from the scale invariant versions. There are fewer reversals in the originals. So do we understand what's going on here? And the answer is we think we do understand what's going on in this column, proportion of ties, but we're still a little bit mystified about why the parameter values create different situations for the next column. So what we did is we looked instead of at pairs of careers, at individual careers. So for this third column in this table, we ran 100 careers, not in pairs. And for each month, we looked whether there was any change at all in the index that month. And it turned out for the Hersch index with these values for P and C, about 90% of the months didn't have any increase at all. Well, that's because we're doing it by the month, and by the month, these are very small numbers, so it's quite likely that you didn't actually fit a larger square. There are fewer months in which the scale invariant version makes no change, which means that the scale invariant version makes more changes more often. Your index increases more often using the scale invariant version, and that's true for every parameter value going down the road. So if we think about more changes as being proportional to the eventual career value, if you divide the career value into more changes, they're smaller changes, proportionately speaking, and that's why we're getting resolution, greater resolution and fewer ties. At least we think that's the explanation for what's going on here. We also looked at robustness. So this was 100 careers, each career lasts 30 years, so 360 months. And scale invariant versions have greater resolution. So we also looked at the standard deviation at the end of these careers, and that's going to represent, like the reversals, a measure of robustness or resistance to noise. And what we found is for the original parameter values, the first pair, indeed, the standard deviation was greater for the original values. The scale invariant versions were more resistant to being influenced by the Poisson noise. But as with reversals, that advantage disappeared for the middle pair and actually went in the other direction for the third pair. So again, we don't really have yet an explanation we necessarily understand or believe for this. So let me end by summarizing what we did here. We took the original Hersch and Wojinger indices. They impose one publication equal one citation as a kind of assumption on all subdisciplines. And our argument is that this is not always appropriate. We took ideas from the Nash bargaining problem to provide scale invariant versions of these indices, and that fixes, we claim, the distortion. We characterized the scale invariant Hersch Index using axioms that parallel those from Nash. Simulations with noise suggested that the scale invariant versions have greater resolution, fewer ties, and also for some parameter values, but not for others, greater robustness. And that's the end of my talk.
Okay, thanks, Bill. So please unmute for a round of applause.
Okay, I can't see the chat right now.
Okay,
Here we go.
Would it be easier for you if you unshare it, or I can read
Okay,
questions for you?
I can unshare.
Can you read it now, or shall I read
I
them for you?
can, but why don't you read it to me?
Okay, so the first question is from Nisarg. So he's asking, what would be a justification for symmetry in this context? The two players, papers, and citations don't seem interchangeable.
Well, what it means is, like the Hersch Index, remember Hersch Index and the Wojcicki Index do satisfy this symmetry. Like the Hersch Index, what this says is, of course, they're not people, but what we're saying is that we're not automatically and necessarily privileging productivity over impact or impact over productivity. Of course, a given record might do that. A given record might have a long, high rectangle or a wide rectangle, but the index itself has no built-in bias towards valuing either of those characteristics of a citation record over the other. That's the best I can say for Y symmetry.
Yeah, thanks, Bill. I was just kind of wondering, I don't think we have like a theoretical answer as to whether two papers with 50 citations each are good, or whether are better, or whether 50 papers with 2 citations each are better. So it would be nice to see some survey of actual researchers and see whether they find one or the other better.
Well, of course, this whole subject would be improved if we looked at real world data. The problem with looking at real world data is it's very hard to get clean real world data. If you look at the Hersch indices that are provided, or the citation records by Google, they're very dirty. When I look at mine, they include multiple versions of the same paper, and they're missing other papers. So, Dominic actually did this for using the Google Scholar, I think, version of the Hersch Index, and the data was kind of interesting. But again, I don't know what it means. That data suggested that most people, but most wasn't nearly all, this is from a relatively small sample, that most researchers actually, when you look at their best fit rectangle, it's very close to a square, but a substantial minority have ones that are significantly different from a square. And one of the researchers is someone in that list, is someone who's known for writing books. And indeed, the rectangle for that person was considerably higher than a square. So some weak evidence of what's going on. My idea is that this would lead to, if this kind of an index were actually used, it would lead to discussions within subdisciplines about what the appropriate limits are on C and P. You might want to not say rectangles could be arbitrarily long and slim like your 50 by 2. Most people wouldn't like that, I think. But the limits might be different for different subdisciplines, and that would be a healthy discussion, perhaps. It would make clear what expectations were in the field.
Thank you.
And what's next?
So we've got a couple more questions that are really pointers to the literature. So there's one from Rida about the paper by Filippini and Motti Perry, how to count citations if you must. So Bill.
Okay, well, I'll be happy to look at that.
So I can say something about this. So this is the Euclidean index, and it scales with the y coordinate, but it does not scale with the x coordinate. So there's some relationship, but it's not very close.
There are also axiomatization. That's why it's interesting, I think, to compare.
Right, so
it probably doesn't satisfy symmetry either then, right, Garrett?
Sorry?
So probably this one does not satisfy symmetry.
It does not satisfy symmetry, but they give another axiomatic characterization in terms of other axioms.
I see.
There's something in there.
One thing we like about our axiomatization is that each of them, and it includes each of the axioms, even the max bounded axiom, has a certain degree of naturality. I mean, some some axiomatizations have the one kicker axiom that is a technical axiom that doesn't have very appealing normative properties. We think all of our axioms are relatively appealing normatively. You can argue against them, but you can argue for them.
So Gerhard also offers some pointers to the literature. So Gerhard, do you want to elaborate on that?
Yes,
Okay.
yes. So the index that you are proposing, it already exists in the scientometrics and bibliometrics literature. There it is called the chi, the Greek letter chi index, but it's not well investigated. I only know 2 papers about it, and the first one is more a computational study that is evaluating a lot of data. Right, it's done by this type of research is done by librarian people working in research libraries. And then there's also an axiomatic characterization, but the axioms there are not half as nice as your axioms.
I see.
So I've put the references into the chat, but I can send them to you directly by email afterwards.
That would also be good. That would also be good. I appreciate it, Gerhard. We actually spoke about this, and I spoke about this idea something like 5 years ago. But that's before we had the axiomatization and before we had the simulation data. Do you know whether anything like the simulations has been done for this resistance to noise?
I don't think so. But this bibliometrics community, they are very different from us. They have very little mathematical contributions, and they are data driven. So right. I do not really know that. I only know a small part of their literature. But there's no need to worry. So your results are much deeper than the known results.
I see. Thanks, that's very helpful.
Right, so in the comments, so Fabian makes an interesting point about how noise may affect publications and citations differently. And I think there's a response to that from Bill's co-author. So perhaps we can skip that. So there's a question from Peter. So Nash has this ingredient of the bargaining powers. Do you want to include that aspect as well?
That's not I'd have to think about that. That's not something I've thought about, because of course P and C are not people with bargaining powers. They're abstract.
Okay, and there's a question from Marcus, which he claims to be too complicated for the chat. So go ahead, Marcus.
Well, if you'd like, I can write it in the chat, but I don't think you want me to do that.
No need.
Okay.
I actually have 2 questions. So, I mean, one question is, so one of the nice things about Nash, although it was originally proposed as a 2-player model, it actually generalizes to n bargaining agents easily. All the axioms generalize, everything works. And so that suggests that you could include more than 2 kinds of information in your citation index. So what kinds of information could you include? So for example, one thing you could include when you're looking at papers or at books is their length, right? So normally we do not consider the length of a paper to be sort of commensurate with the number of papers or the number of citations, but the beauty of your model is it doesn't have to be commensurate. That's the whole point of it.
That's right.
Right. So you could consider it as an additional measure of quality, right? Ceteris paribus, a 15-page paper has more content than a 10-page paper, right? This is why editors often tell people to shorten their papers, because they'll say to them, well, your result is nice, but it doesn't really need a 30-page paper. You could probably do this in 20 pages, right? We often hear that kind of. Another thing that you could look at if you're measuring the quality of a single researcher is you can normalize papers by the number of co-authors, right? I mean, theoretically, your scientific contribution to a paper with with 1 co-author is less than your scientific contribution to a paper with 50 co-authors, right? Again, that's the kind of thing that you couldn't do if you had to treat all the different dimensions on par, but you don't have to do that.
Journal quality too.
Journal, that's more difficult to measure because that's kind of begging the question, how do you measure the journal quality, right? By citation count. But yeah, maybe something like that. There could be a bit of a circularity there, but those are other things you could consider. Also the age of the paper, right? So I mean, a paper which is 30 years old just mechanically is going to have more citations than a paper which is 6 months old, right? And so that's another thing that you could correct by. Which takes me to my second point, which is that your last axiom was basically that you wanted your your citation index to play nicely with this, what you called the simple deterministic model, right? Now, the simple deterministic model, we all agree is ridiculous. That's not how citations grow over time. I think a slightly more realistic model, I'm not saying it's totally realistic, but I think it's more realistic. I think it's well known that publications, citations have a sort of what's called a Matthew effect. In other words, papers which get cited a lot tend to get cited a lot because everybody's already seen them, right? So there's a sense in which citations grow exponentially over time, right? The growth rate of the citation count of a paper is proportional to its current number of citations.
For a while. Is that does
yeah,
that
for a while, yes.
Then there's time?
Yes, so this is true that after a while papers become obsolete or they get forgotten or whatever. But at least for a while, one could fit the curve with an exponential growth curve, right? And then in some sense, the relevant number is not the slope of the curve, it's the exponential rate. In other words, it's the logarithmic slope, right? The logarithmic slope, just like if you look at it like, we're all familiar with pandemics right now. So it's kind of like it's the R value of the pandemic model, right? So that might be something that you could use as a more accurate measure of the kind of growth rate of citations over time. And then the question would be, if you replaced your sixth axiom with an axiom which says that it plays nicely with this kind of logarithmic slope, what happens then? What kind of citation?
The answer is, if we leave out linear growth, we get a class, if I remember this correctly, and I have to check, we get a class of axioms that include all the powers of the Hersch Index. So we can handle different powers very easily. If you wanted it to be quadratic, you could make it quadratic. If you wanted it to be 3/2 power, you could make it 3/2 power. So it can be any power of the size of the area of the inscribed rectangle. But that's not the same as logarithmic. I don't think you can get that from the things we've done.
Right. I'm not suggesting a logarithm of the citation index. I'm suggesting that you apply a logarithm to the growth rate of citations over time, and that's what would be used as the measure of the sort of the growth rate of citations. And the question is, if your last axiom says that you sort of have to be compatible with that, then what citation index would you get?
I think look, no one would dispute your case, your argument, and certainly I don't think Hersch would, that the simple deterministic model is not at all realistic. But I don't think the argument that you should use linear growth depends on it being realistic. It makes the side length seem rational, even if the model is not realistic. Now,
okay.
You might be arguing that it doesn't fairly compensate junior versus senior people. That's the argument you'd have to make, that you need something else to do that.
Right, and the question then is, what is fair compensation? Which means, what is the correct measure to sort of scale time against citations?
Right, that's right. And of course, that could be examined in the real world, right? By looking at people early in their careers versus late in their own careers. Comparing people against themselves would seem to be the best way to do that, right? Because you're getting other factors out of there by doing that. Again, this requires having cleaned up real world data. So maybe I can find someone in the community that Gerhard was talking about who'd actually be interested in collecting a lot of numbers and looking at detailed publication records. I was not interested in doing this.
Okay, thanks, Bill. I think we are getting to the end of our time slot. Sure. So I just wanted to remark that there are lots of interesting links in the chat from Gerhard, but also from others. So I think this chat has a lot of value. Unfortunately, the chat gets saved with the talk. So that would be something to explore later. Also questions that I'm afraid we don't have time for.
I see.
Okay, so before we wrap up for today, so I just want to make an announcement about next week. So Ulla sent an email to those of you who are on the mailing list for the seminar. So next week we have one of our more exciting events, which is a rump session. So unfortunately, it will not be chaired by Ulla. So Ulla is kind of the best rump session master I ever met. So he can run them perfectly. So I will be trying to emulate him next time. I will do a much better job at keeping people to the time limit, which will be 5 minutes compared to what I did today. I don't think I was particularly successful today in that regard. Right, so the format will be 5 minutes for the talk, 1 or 2 minutes for questions. So we are planning for 8 talks. We already have about 4 or 5 speakers. We still have some slots. So if you have some exciting work that you can reasonably summarize in 5 minutes, do please sign up. So there's a form on the seminar's website. Right? There's also a link in the email if you're on the mailing list. So I encourage everyone, in particular junior people, but not only, to present their work in this format. So it's going to be fun. And of course, all of you are more than welcome to attend next time. So see you next week. Thanks.
So Edith, are you still there?
Yes.
How many minutes did I take for my talk?
25.
Okay.